There is a galaxy in the southern sky, in a faint constellation called Fornax, that is burning with the light of hundreds of millions of suns. It sits so far away that its light has been travelling toward us for more than 13 billion years. And when astronomers finally measured how far back in time they were seeing, the number came back wrong. Not slightly wrong. Wrong in a way that should not be physically possible. This galaxy is shining at us from a moment when the universe was less than 300 million years old, barely 2% of its current age, and it is already too big, too bright, and too chemically rich to exist. The models that describe how galaxies are built say it needed billions of years. It had a few hundred million. And yet, there it is. Its name is JADES-GS-Z14-0, and by every rule we thought we understood, it should not be there. If a real object breaking the timeline of the universe is the kind of thing that keeps you up at night, hit that like button and subscribe, because tonight we are going all the way down into what the James Webb Space Telescope found, and why some of the people who built our picture of the cosmos quietly stopped sleeping. Tell me in the comments where in the world you are watching from and what time it is where you are right now. Then dim the lights. We are about to fall backward through 13 billion years. Let me start by giving you the universe you already trust, the one in the textbooks, the one that, until very recently, almost everyone agreed on. It begins with the Big Bang, not an explosion in space, but an expansion of space itself, everywhere at once, about 13.8 billion years ago. In the first fraction of a second, everything that would ever become a star, a planet, a person, was compressed into a state hotter and denser than anything that exists today. Then it expanded, it cooled, and for the first few 100,000 years the whole universe was a glowing fog, too hot for atoms to hold together, an ocean of loose particles and trapped light. Then, about 380,000 years in, the fog cleared. The universe cooled enough for protons and electrons to finally join into the first neutral hydrogen atoms. The universe had cooled enough to allow the early nuclei to pull in electrons and form neutral atoms, a moment called recombination, although it actually marks the first time these particles ever combined. And when that happened, light was set free. That first light is still travelling today. We call it the cosmic microwave background, and it is the oldest thing any instrument has ever seen. After that came the strangest chapter of all, a time with no stars, no galaxies, no light being made anywhere. This moment ushered in a period we now call the Cosmic Dark Ages, a time when the universe was enveloped by a fog of neutral hydrogen. Picture the entire cosmos as an unlit house at midnight, every room full of cold, invisible gas, waiting. Nothing to see, nothing to be seen. This darkness lasted for a very long time by human reckoning, though it was only a blink in cosmic terms. And then the first lights came on. The cosmic dawn marks the time when the first stars, galaxies, and black holes ignited, ending the cosmic dark ages. Gravity had been patiently pulling the gas together into denser and denser clumps, and when a clump got dense enough and hot enough at its center, it caught fire. The first stars were born. They flooded the darkness with ultraviolet radiation, and slowly, bubble by bubble, they burned the fog away until the universe became transparent, the clear cosmos we live in now. Here is the part I need you to hold on to, because everything tonight turns on it. In this picture, galaxies are not born large. They are assembled slowly from the bottom up. In the very early universe, tiny density fluctuations seed slightly overdense regions. The smallest overdensities collapse first, forming low-mass dark matter halos, and these small halos then merge with each other and accrete additional matter, building progressively larger structures over cosmic time. Small things merge into bigger things merge into bigger things still. Smaller galaxies merge to make bigger galaxies, like tributaries converging to form a large river. That river metaphor is worth sitting with, because it captures the whole logic of the accepted model. A great river does not appear fully formed at its mouth. It starts as 1,000 tiny trickles high in the mountains, and only after a long journey downhill do those trickles gather into something wide and deep and powerful. A galaxy the size of our Milky Way is supposed to be the mouth of that river. Behind it lies billions of years of gathering. You cannot get the wide river without the long journey. The journey is the point. Where the analogy breaks is that a river flows in space while galaxies flow in time, and time, we believed, could not be rushed. So the beautiful settled picture is this: a cold beginning, a long dark, a slow dawn. Then billions of unhurried years of small things becoming large things, the cosmic web of dark matter acting as the invisible scaffolding, patiently pulling ordinary matter into place. It is elegant. It matches the cosmic microwave background almost perfectly. It predicts the distribution of galaxies across the sky with astonishing accuracy. For decades, it worked. And notice what that entire story quietly depends on: timing. Everything in this model is a clock. Galaxies at a given age are supposed to look a certain way, hold a certain mass, contain a certain mix of elements, because they have had exactly so much time and no more. The universe hands out time in equal measure to everyone, and time is the one thing no galaxy can borrow, steal, or skip. The clock, we believed, was sealed. You cannot build the river faster than the water flows. File that away. The clock was supposed to be sealed. To understand why anyone would panic over a smudge of red light, you have to understand how astronomers read the age of the cosmos, and it comes down to a single, almost unbelievable fact. When you look far away, you are looking into the past. Always. There is no way around it. Light is fast, but it is not infinitely fast. It travels at about 186,000 miles every second, and not 1 inch faster. That speed is a hard wall built into reality. So when you look at the moon, you are not seeing the moon as it is now. You are seeing it as it was a little over a second ago, because that is how long its light took to cross the gap. Look at the sun, and you are seeing 8 minutes into the past. The sun could have vanished 8 minutes ago, and you would have no way of knowing yet. Now stretch that idea until it groans. Think of light from a distant object as a letter mailed to you across an enormous distance. The farther away the sender lives, the longer the letter spent in transit, and the more out of date its news is by the time it lands in your hands. A letter from across town tells you about yesterday. A letter from the other side of the world might describe events from weeks ago. And a letter that took 13 billion years to arrive is not describing the sender as they are now. It is describing a person, a place, a galaxy that existed 13 billion years ago and has long since changed beyond recognition or died entirely. Every telescope is a mailbox stuffed with letters from the dead. The analogy cracks in one dizzying place. The senders of these letters are not just far away in space. They are gone in time, and the version of them we read about no longer exists anywhere in the universe. Astronomers call this look-back time, and it turns every big telescope into a machine that sees backward. The James Webb Space Telescope, the most powerful ever built, was designed for exactly one purpose above all others: to catch the oldest, faintest, most stretched out letters ever sent. To read the news from the dawn of everything. That stretching matters, and it is the second half of the trick. The universe is not just big, it is expanding. Every point is racing away from every other point, and the space in between is growing. So while a beam of ancient light is crossing that space, the space itself keeps stretching, and it drags the wavelength of the light out longer and longer along with it. Light that left a galaxy as brilliant blue-white ultraviolet arrives at us shifted all the way down into the red and the infrared, its wavelength pulled long like a rubber band. The light travelling millions and billions of light years across the universe is stretched by the expansion of the universe, and this stretching is known as redshift. The more the light has been stretched, the farther it has travelled, and the deeper into the past you are seeing. Astronomers put a number on that stretch and call it redshift. A small redshift means a nearby recent galaxy. A large redshift means an ancient one. And here is the quiet cruelty hidden in this whole beautiful system. The thing that turns a discovery into a crisis. The farther you look, the less time the universe had. Read that again, slowly. When Webb captures a galaxy at the very edge of what is possible, it is not just seeing something far away. It is seeing something that existed when the entire cosmos was only a few 100 million years old. A galaxy at that distance had almost no time to do anything at all. No time to gather, no time to grow. No time to build up generations of stars, forge heavy elements, and settle into a mature adult shape. The deeper the letter came from, the younger the universe was when it was written, and the smaller and simpler and more unfinished its author had to be. That was the promise and the trap all in one. Point the most powerful eye ever built at the deepest reachable past, and you should see the universe in its infancy, faint, small, just beginning. Baby galaxies barely started. That is what the model demanded. That is what everyone expected to find. On the 11th and 12th of July 2022, we finally opened the mailbox. The first image Webb released to the world was a deep field, a single patch of sky so small that, as the team liked to describe it, it was approximately the size of a grain of sand held at arm's length. A tiny sliver of the vast universe. They chose a spot centered on a distant cluster of galaxies called SMACS 0723, and they let the telescope stare. This deep field was a composite made from images totaling 12.5 hours, achieving depths beyond the Hubble Space Telescope's deepest fields, which had taken weeks. 12.5 hours against Hubble's weeks. In a fragment of sky the size of a sand grain, and it was flooded. Webb's first deep field, galaxy cluster SMACS 0723, was teeming with thousands of galaxies, including the faintest objects ever observed in the infrared. Thousands of them in a speck of nothing. Some appeared as arcs and smears, their light bent and magnified by the gravity of the cluster in the foreground, a natural lens made of mass. The wonder in the room was real. Here, at last, was the deep past coming into focus, sharper than anyone had ever seen it. Here was the promise Webb had been built to keep, the first galaxies, the opening pages of the cosmic story. But look closely at that image, and scattered through the swarm you would notice them, tiny points, faint and red. Redder than they had any right to be. Little dots of deep crimson light, so small and so unremarkable at first that nobody could yet say what they were. These unexpected objects came into view in JWST's first data release in 2022, thanks to its sharp images and sensitivity in the near infrared. They stood out for being extreme, extremely red, extremely compact, and extremely wrong for a universe that was supposed to hold only faint, blue, unfinished infants at these depths. Within days, the email started flying between observatories. Teams around the world downloaded the raw data the moment it went public and began the frantic work of measuring how far away these objects really were. As soon as data from JWST became publicly available in early July 2022, preprints started to be posted, and bright, high redshift galaxies were being reported. The excitement was electric. Then the redshifts began coming back, and the mood in the room changed. Because the numbers were too high. The galaxies were too far, which meant they were too early, which meant the universe had been too young when their light left them. And they were too bright, which meant they held too many stars, which meant they had somehow assembled far too much mass in far too little time. The letters from the dawn of everything were describing something that, according to the sealed clock, could not have been written yet. Along with the reports came a growing concern that these galaxies were not abiding by the laws of standard cosmology. That unease, that first cold prickle at the back of the neck when a measurement refuses to behave, is where the real story begins. Because one strange galaxy is a puzzle, a telescope full of them is something else entirely. There was a man named Ivo Labbé, an astronomer at Swinburne University of Technology in Australia, and he and his colleagues were among those who pounced on the fresh data. Within days, Labbé and his colleagues had spotted about a dozen objects that looked particularly bright and red, a sign that they could be massive and far away. His colleague Erica Nelson at the University of Colorado Boulder described the experience in words that stick with you. "They stand out immediately. You see them as soon as you look at these images," she said. "You did not have to hunt for these things. You opened the file and they were staring back." Then they did the math on how much mass those objects had to contain to shine that brightly from that far away, and the room went quiet. 6 of the objects looked like they came from no later than about 700 million years after the Big Bang, and 6 of them held staggering amounts of stars. Those galaxies appeared to hold up to 10 billion times the mass of our Sun in stars, and one of them might contain the mass of 100 billion suns. 100 billion suns. That is roughly the entire stellar mass of the Milky Way, the grand spiral we live in, a galaxy that has had more than 13 billion years to grow. And here was its twin, apparently, fully formed, when the universe was still a toddler. Labbé put the problem in a single sentence that should chill anyone who understands what it means. Adding up the stars in those galaxies, it would exceed the total amount of mass available in the universe at that time, he said. Then, with the calm understatement of someone who knows he is standing at the edge of something, he added, "So you know that something is afoot." Sit with that for a second. It is not that these galaxies were surprisingly large. It is that, on the first pass, they seemed to contain more matter than the young universe was supposed to have made available to build them with. As if you walked into a bakery an hour after it opened and found a wedding cake taller than the building, made from more flour than the whole city had milled that morning. The team published their findings in the journal Nature in February of 2023, and the words they used were not hedged the way scientists usually hedge. We expected only to find tiny, young, baby galaxies at this point in time, but we've discovered galaxies as mature as our own in what was previously understood to be the dawn of the universe, Labbé said. And then the line that ricocheted around the world. The 6 galaxies we found are more than 12 billion years old, only 500 to 700 million years after the Big Bang, reaching sizes up to 100 billion times the mass of our Sun. This is too big to even exist within current models. Too big to even exist. That was a lead author of a Nature paper, saying out loud what the data was screaming. But science does not run on the single dramatic sentence, and this is where the story gets more honest and, in a strange way, more unsettling. Because the first reaction of a good scientist to an impossible result is not celebration. It is suspicion. Suspicion of the instrument, suspicion of the method, suspicion of themselves. And Webb, in those first months, was a brand new machine still learning to see. With new telescopes comes the natural growing pains of calibration and data reanalysis, and calibrating the instruments aboard JWST is a critical step to ensure the data can be interpreted accurately. There was a real problem here, and the community knew it. The distances of these 6 galaxies had been estimated from their brightness across a handful of colour filters, a fast method, but a rough one. In their quest for quick results, researchers relied on redshift estimates derived from simple brightness-based measurements, which are easier to obtain but less precise than direct measurements of redshift. And that rough method could go badly wrong. A cool, dusty, ordinary galaxy sitting relatively nearby can, in the wrong filters, masquerade as a monstrous galaxy at the edge of time. The colours lie. Nathan Adams, an astronomer at the University of Manchester, ran the recalibrated numbers on some of the early candidates, and found the danger was not theoretical. He and his colleagues found there could be dramatic changes, with one galaxy at a redshift of 20.4 recalibrated to a redshift of just 0.7. That is the difference between a galaxy at the dawn of the universe and a galaxy practically in our own backyard. His plea to the community was almost weary. "We need to calm down a little bit," Adams said. "It's a bit too early to say we've completely broken the universe." So the doubt was reasonable. Maybe it was all a mirage of a young instrument and a rushed method. Maybe the dead had never written those letters at all, and we were misreading the postmarks. For a while, that hope held. Recalibration shaved some galaxies back down. Some of Labbé's 6 turned out to be less extreme than the first alarming estimate. The universe seemed to exhale. And then came the spectra. A brightness estimate is a guess. A spectrum is a confession. When you spread a galaxy's light out into its full rainbow of colours and read the individual lines burned into it by specific elements, you are no longer guessing at its distance. You are measuring it directly, with almost no room to hide. The catch is that spectra take enormous amounts of telescope time, hours upon hours of staring at a single faint smudge. But Webb had the time, and one by one, The team pointed it at the most extreme candidates and demanded the truth. The truth held. When astronomers took spectra of galaxy after galaxy at these terrifying distances, the high redshifts were confirmed. These were not dusty imposters lurking nearby. They really were there, at the dawn of time, bright and massive and impossibly early. The mirage refused to dissolve. And that is the moment the doubt curdled into something colder. Because a mistake you can fix. A mistake is almost a relief. But a confirmation, repeated, from the best instrument ever built, with the most direct method available, leaves you with nowhere to run. The galaxies were real, which meant the problem was real, which meant that somewhere in our beautiful, settled, decades-old picture of how the universe builds itself, something was broken. And the deeper Webb looked, the worse it got. Because scattered through those same deep fields were the little red dots. The faint crimson points nobody could name in that first image had, by the summer of 2023, become their own full-blown mystery. By summer of 2023, a number of discovery papers had identified 3 traits in common among them. They were compact in size, they had unusual V-shaped spectra, and they showed emission from high-velocity hydrogen gas. They were not rare either. A few appeared in every pointing of the JWST imaging camera, accounting for a few % of all known galaxies in the first billion years of cosmic time. Whatever they were, the early universe was full of them. The trouble was that nobody could agree on what they were. And the 2 leading answers were both nightmares for the standard picture, in different ways. The first idea was that the little red dots were galaxies. Overgrown, star-stuffed galaxies, so packed with stars in so tiny a volume that they would be, in the words of one researcher, the densest galaxies in the universe. That was the problem. The analysis suggested little red dots are simply too luminous and too compact to be explained by a large number of stars. And if they were purely made of stars, they would be the densest galaxies in the universe. An absurd concentration of matter jammed into a point in an era when there had barely been time to make stars at all. The second idea was, if anything, stranger. Maybe the light was not coming from stars. Maybe it was coming from monsters. Supermassive black holes, already grown enormous in the infant cosmos, blazing as they devoured the gas around them. Debate quickly emerged. Some researchers favoured the star-rich galaxy idea, while others argued the little red dots were actually active galactic nuclei, which occur when material spirals into a galaxy's central black hole, forming an extremely hot accretion disk. But that interpretation had its own impossible bill to pay. The scenario required these objects to host supermassive black holes, with extremely large masses, and far more of them than expected, considering how many little red dots the telescope was finding. Enormous black holes, in enormous numbers, far too soon. Think about what that fork in the road actually means. On one side, a galaxy so dense it defies belief. On the other, a giant black hole that should not have had time to grow. Both answers demand that the young universe did something it was not supposed to be able to do. And for a long stretch, the most honest thing anyone could say was that they did not know which nightmare was true. We had found thousands of glowing objects in the deep past, and we could not tell whether we were looking at swarms of stars or the hidden throats of black holes. Not far away, not fuzzy, right there in the sharpest images ever taken, and we could not name them. Very recently, in early 2026, the balance began to tip. A study drawing on the highest quality Webb spectra of these objects argued that the strange, broad shapes of their spectral lines were not caused by gas whirling around at tremendous speed, but by light bouncing off dense clouds of electrons before it escaped. In most objects studied with the highest quality spectra, the lines are broadened by electron scattering with a narrow intrinsic core, and the data require very high electron column densities and compact sizes, which can be explained only by black hole accretion. In plain terms, the leading interpretation now is that many little red dots are young, growing, supermassive black holes, wrapped in suffocating cocoons of hot gas that hide their usual screams of X-rays and radio waves. As one of the researchers put it, without the ionized gas, The data simply don't make sense. That may rescue the star counting problem, but notice what it quietly concedes. It trades a crisis of too many stars for a crisis of too many black holes, grown too fast, too early. The nightmare did not vanish. It changed shape. And even the scientists announcing the result admit the story is not closed. Even if the little red dots mystery has been solved and cosmology's reigning paradigm saved, a host of new questions would arise. But step back from the dots for a moment, because underneath all of it, feeding both the massive galaxies and the hidden black holes, is a single problem, the oldest and hardest one. It is not really a problem of size, it is a problem of time. Let me make the timing problem physical, because numbers alone will not do it justice. The confirmed record holder, JADES-GS-Z14-0, the galaxy we opened with, is the cleanest example we have. It is not a candidate anymore, it has been nailed down. Its light left it when the universe was less than 300 million years old, and that distance has been pinned with astonishing precision, confirmed independently by the detection of oxygen in it, using the ALMA telescope array in Chile. It is so far away that its light took 13.4 billion years to reach us, meaning we see it as it was when the universe was less than 300 million years old, about 2% of its present age. Now here is the part that broke people. That galaxy is not a faint little seed. The copious amount of starlight implies it is massive and is over 1,600 light years across. And such a luminous, massive and large galaxy at cosmic dawn defies current understanding of galaxy formation. It is bright, it is broad, and crucially, it is chemically enriched. Astronomers found oxygen inside it. And oxygen is not something the universe starts with. The Big Bang made hydrogen and helium, almost nothing else. Every oxygen atom in existence, including the ones in the air you are breathing right now, was forged in the core of a star and then blasted out into space when that star died. So to find oxygen already present in a galaxy means that inside it, entire generations of massive stars had already been born, lived their whole lives, and exploded, seeding the gas with the ashes of their deaths. The presence of oxygen so early in the life of this galaxy is a surprise, and suggests that multiple generations of very massive stars had already lived their lives before we observed the galaxy. Multiple generations, born, aged, and dead, in under 300 million years. Let me translate that into a timescale your body can feel. Imagine the entire history of the universe, all 13.8 billion years, compressed into a single calendar year. On that scale, the Big Bang is the first instant of January the 1st. You, right now, are the final stroke of midnight on December the 31st. Everything human, all of recorded history, is the last fraction of a second before the new year. On that calendar, 300 million years is not even a week. It is the first 8 days of January. And in those first 8 days, this galaxy had already built itself, filled itself with hundreds of millions of suns, and cooked up multiple full cycles of stellar life and death. The lead author on the study of that galaxy, Stefano Carniani, estimated that JADES-GS-Z14-0 appears to have reached the stage of evolution we see now in about 10 million years, and if that's confirmed, it will be necessary to review theoretical models of galactic evolution. That is, the model's first honest crack. Not a smudge that recalibration can erase, a confirmed, oxygen-bearing, fully lit galaxy in the first week of the cosmic year, doing something the slow river model of galaxy building says takes months. The team's own conclusion did not try to soften it. All of these observations, together, tell us that JADES-GS-Z14-0 is not like the types of galaxies that have been predicted by theoretical models and computer simulations to exist in the very early universe. And they had found no suitable analogues from the hundreds of other high redshift galaxies in their survey. No analogues, nothing else like it. A galaxy that stands alone against the theory. So what exactly is the theory it stands against? To understand why a bright dot of oxygen-rich light can shake the foundations of cosmology, you have to meet the model by its name. It is called Lambda-CDM. It is the standard model of the universe, the reigning champion, and for a generation it has been almost untouchable. The letters matter. The CDM part stands for cold dark matter, the invisible substance that outweighs all the ordinary matter, all the stars and gas and planets and people, by roughly 5 to 1. We cannot see it.
We cannot touch it.
But we can feel its gravity everywhere, and without it, the universe simply does not work. Here is why. Run the calculations for a universe made only of ordinary matter, and you get a disaster. When scientists run these simulations without dark matter, the regular gas never clumps fast enough to form galaxies before the expansion of the universe pulls everything too far apart, and the universe would be a thin, featureless soup of gas. No galaxies, no stars, no us. Ordinary matter alone cannot beat the clock. It cannot pull itself together fast enough against the relentless stretching of space. Something invisible had to go first, had to start clumping earlier and harder, to build gravitational wells deep enough for ordinary gas to fall into and ignite. That invisible something is the scaffolding of the entire cosmos. The universe's matter is organized into a vast cosmic web of interconnected filaments, sheets, and voids, and dark matter is the scaffolding for all of this, forming halos that act as potential wells, pulling in ordinary matter. Think of building a skyscraper. You do not start with the glass in the offices. You start with a steel skeleton, an invisible from the street framework that goes up first and defines where every floor, every wall, every window will eventually hang. Dark matter is that skeleton. Ordinary matter, the stuff that shines, is just the cladding bolted on afterward, filling in a shape the dark matter drew first. Where the analogy fails is that a skyscraper's frame is rigid and finished before the walls go up, while the cosmic web's scaffolding is still slowly growing and clumping even as the galaxies form inside it, the whole structure assembling itself in motion. And that scaffolding has a schedule. This is the crux of everything. The dark matter clumps grow at a pace set by gravity and the expansion rate of the universe, and that pace is not negotiable. In the early cosmos, the scaffolding was still sparse. As Lebesgue himself explained the standard picture, when dark matter clumps together into a halo, it attracts gas which forms a galaxy and its stars. But this process is supposed to take a long time, and in the early universe, there's just not that many clumps of dark matter. Not many clumps. Small clumps. A skeleton barely started. And you cannot hang the whole facade of a skyscraper on 3 floors of frame that have not been built yet. This is why a single, massive, early galaxy is so dangerous. There is a hard ceiling built into the model, and it is not a matter of opinion. A galaxy can only be made of the ordinary matter that has fallen into its dark matter halo, and the amount of ordinary matter available is a fixed fraction of the halo's total mass. So the abundance of dark matter halos at any given moment sets an absolute upper limit on how much starlight the universe is allowed to contain at that moment. An astronomer named Michael Boylan Colchin at the University of Texas at Austin spelled this out in a landmark paper with a title that tells you the mood. Stress testing the standard model. The stellar mass of a galaxy is limited by the available baryonic reservoir of its host dark matter halo, and the mass function of dark matter halos therefore imposes an absolute upper limit on the number density and stellar mass density of galaxies more massive than a given mass at any epoch. An absolute upper limit. A wall. And when he checked the most massive early galaxy candidates against that wall, they were not comfortably inside it. He showed that the most massive galaxy candidates in JWST observations lie at the very edge of these limits, indicating an important unresolved issue with the properties of the galaxies, how galaxies form at early times in the standard model, or within this standard cosmology itself. Read that last clause again, or within this standard cosmology itself. He was laying out 3 possible culprits, and one of them was the model of the universe. To press it right up against the wall Some of the early candidates implied that the young universe had converted nearly all of the ordinary matter in a halo into stars. Almost every available atom turned into starlight. And that is a red flag of the deepest kind. Because real galaxies are wasteful, sloppy things. 6 massive galaxy candidates with stellar masses beyond 10 billion suns implied baryon to stellar conversion ratios approaching unity, several orders of magnitude brighter and more massive than the standard prediction. A conversion ratio approaching 1 means near perfect efficiency, and in our universe, star formation is anything but efficient. Normally, a galaxy turns only a small fraction of its gas into stars before winds and explosions blow the rest away. To approach total efficiency, the early universe would have had to be building stars in a way we have never seen anywhere in any era before or since. So which is it? That is the fork the whole field now stands at, and it is worth naming plainly because the honest scientists disagree, and the disagreement is the story. Either the recipe is broken, meaning galaxies in the early universe built stars in some radically different, radically faster way that our simulations never captured. Or the clock is broken, meaning our very timeline of the cosmos, the sealed clock we trusted, is wrong about how much time there was. Most researchers are betting hard on the recipe. And there is a genuinely compelling version of that bet, one that saves the standard model by proposing that the early universe was simply a far more efficient factory than the calm, modern cosmos we live in. The leading idea has a name that sounds almost gentle for something so violent. Feedback-free starburst. JWST observations indicate a surprising excess of luminous galaxies at these depths, consistent with efficient conversion of accreted gas into stars. And the high densities and low metallicities at this epoch guarantee a high star formation efficiency in the most massive dark matter halos. The insight is subtle and beautiful. Normally, when stars begin to form in a cloud, the biggest of them quickly start to push back, blasting the surrounding gas with radiation and eventually exploding as supernovae, scattering the raw material before most of it can collapse into more stars. That pushback is the feedback, and it is what keeps star formation slow and wasteful. But there is a narrow window. There is a natural window that lasts about 2 million years between a starburst and the onset of effective stellar wind and supernova feedback. And if the gas in the early universe was dense enough, it could collapse and form stars in less time than that window, finishing the job before the feedback ever kicked in. Star formation running to completion before anything could stop it. A fire that burns to the end before the alarm even sounds. If that is right, then the universe did not break its own clock. It just lit an unimaginably efficient fire in the first weeks of the cosmic year, and Webb caught the flames. Reassuringly, in mid-2024, the official verdict from several teams was that the standard model would probably survive. Some galaxies appear to have grown so massive so quickly that simulations couldn't account for them. But a newer study found that some of those early galaxies are in fact much less massive than they first appeared, brightness enhanced by both bursty star formation and light from active supermassive black holes within them. Probably. Some. In fact. Notice how much weight those quiet words are carrying. Because for every paper that pushes the crisis back into its box, another arrives that pries the lid open again. The feedback-free starburst idea itself, even its own authors admit, demands conditions we have never directly confirmed. And the newest studies find that the simplest versions of it require values so extreme they strain belief. Neither of the two leading scenarios alone is likely to explain the observations, since they require extreme values that are typically not predicted by current simulations. The rescue works, but only if the universe was stranger and more violent at its dawn than anything we can yet reproduce. We have not saved the model so much as forced it to confess that we never really understood the first chapter at all. And that confession is where the ground truly starts to shift. Because if the recipe was that different at the beginning, if the fires burned that hot and that fast, then the picture of a slow, patient, bottom-up universe, the river gathering itself gently over billions of years, was never the whole truth. there was a violence at the dawn we did not see coming. The clock might be intact, but the thing it was measuring turns out to have been racing. Racing is the right word for what happened next, and not only in the galaxies, it describes the people too. Because once the spectra confirmed those first monsters, a strange kind of dread settled over the collaborations that had built their careers on the slow river universe. Not the loud dread of a disaster movie, the quiet, sick dread of a professional watching a foundation crack under a building they helped design. These were not outsiders sniping at the standard model. These were the insiders. The very people who trusted it most were the ones staring at the impossible numbers on their own screens. Go back to those first frantic weeks of the summer of 2022 and picture the actual scene. Not a control room with red lights flashing. Astronomers hunched over laptops in offices and kitchens across a dozen time zones, downloading the same raw files the instant they went public, running the same code, and arriving at the same disturbing answer independently. Preprints, the rough drafts scientists post before formal peer review, started appearing within days of each other. Bright galaxies, high redshifts, too many, too early. The field was not calmly deliberating, it was scrambling in real time to figure out whether the universe had just contradicted itself. Ivo Labbé and his team were at the front of that scramble, and their dozen bright red candidates became the flashpoint. When they finished the mass estimates, the story you already heard emerged in full. 6 objects, apparently, from the first 700 million years, some carrying the weight of 100 billion suns. And when Labbé summed the starlight and compared it to the ordinary matter the young universe should have had on hand to build with, the total ran over budget. There was, on that first pass, not enough matter in the infant cosmos to account for the stars he was seeing. That is the sentence that sent the panic through the collaboration. Not a galaxy that was surprisingly heavy, but a galaxy that seemed to weigh more than the universe could afford. Now, panic among scientists does not look like screaming. It looks like rechecking. Obsessively. The first instinct of everyone in that Nature paper, and everyone racing them to publish, was to assume they had made a mistake and to hunt for it. And there was a very real place for a mistake to hide. Those first distances were photometric estimates, which is a technical way of saying they were guessed from how bright the objects looked through a small set of coloured filters. It is fast, it is cheap, and it is treacherous. A modest, dusty galaxy sitting relatively close to us can, through the wrong filters, wear the exact same red disguise as a titan at the edge of time. The colours of the two can look nearly identical, even though one is a quiet local and the other is a monster from the dawn. This is the trap that nearly deflated the whole affair, and it deserves respect, because the skeptics were doing exactly what good scientists should. Nathan Adams at the University of Manchester recalibrated some of the earliest candidates and watched them collapse. One object first pegged at a redshift at 20.4, meaning almost the beginning of everything, was reanalyzed and dropped to a redshift below 1, meaning practically our own neighbourhood. That is not a small correction. That is the difference between a letter from the first days of the cosmos and a postcard from down the street. Adams told the community to slow down, to breathe. It was too early, he said, to claim we had broken the universe. For a season, that caution won. Recalibrating Webb's brand new instruments, still settling into their final performance, trimmed several of the wildest candidates down to something less alarming. A few of Labbé's 6 softened under scrutiny. The overrun on the matter budget eased. And you could feel the field wanting to exhale, wanting this to be nothing more than the growing pains of a young telescope learning its own eyes. But a photometric guess can be wrong. A spectrum cannot hide. And so, one by one, they demanded the confession. To pull a spectrum from one of these faint smudges, you spread its light into a full rainbow and read the fine dark and bright lines stamped into it. The fingerprints of specific elements shifted bodily toward the red by the expansion of space. Measure how far those fingerprints have slid, and you have the distance, directly, with almost nowhere left to argue. The cost is time. Hours of the most expensive telescope ever built, staring at a single dot barely brighter than the dark around it. But Webb had the hours, and the team spent them. The confession held. Galaxy after galaxy, when the spectra came back, the terrifying distances were confirmed. These were not dusty locals in disguise. The fingerprints of their elements were slid all the way down into the deep infrared, exactly as a true child of cosmic dawn demands. The imposter theory failed. The mirage would not dissolve. And that is the precise moment the mood in the field changed for good. The moment doubt stopped being a comfort and became a problem. Because doubt, at first, is a friend. Doubt means maybe it was a mistake, and a mistake can be fixed. And if it can be fixed, then the universe still makes sense, and everyone can go home. But a confirmed result, arrived at independently by rival teams using the most direct method available, strips that comfort away. There is no error to find. There is only the thing itself, sitting in the data, refusing to be a mistake. The escape hatch closed. What had been an exciting anomaly, the kind of puzzle careers are made of, hardened into something heavier. A crisis. Not a word astronomers throw around lightly, and they began throwing it around anyway. And the deeper Webb stared, the more the crisis multiplied. Because it was not just the giant galaxies, it was the little ones. The faint crimson points scattered through that very first deep field, the ones nobody could name, had by the summer of 2023 grown into a mystery all their own. The little red dots. They earned that plain, almost childish name honestly. Compact enough to look like points rather than smudges. Red, deeply and strangely red. And everywhere. A handful turned up in nearly every patch of sky Webb photographed, until they made up a few % of every galaxy known from the first billion years. The early universe, it turned out, was speckled with these things. Whatever they were, there were multitudes of them. That was the trouble. Nobody could say what they were, and the two best guesses were each their own kind of horror for the standard picture. Read one of these little red dots as a galaxy, and you get an object so tightly packed with stars that it strains the imagination. The light is too bright and too concentrated in too small a space to be built comfortably from stars alone. Push that interpretation to its conclusion, and you are forced to call them the densest galaxies in the universe, a suffocating crush of suns jammed into a volume that should not be able to hold them, and all of it assembled in an era with barely enough time to make stars at all. Read the same dot the other way, and the light is not from stars, it is from something feeding. A supermassive black hole, already grotesquely large in the infant cosmos, blazing as matter spirals into it and superheats on the way down. That reading has its own bill, and it is monstrous. To explain how many little red dots Webb keeps finding, the universe would need enormous black holes in enormous numbers, grown to giant sizes far, far sooner than any model of black hole growth allows. Either answer breaks a rule. One demands stars we cannot build fast enough, the other demands black holes we cannot grow fast enough. The young universe, it seems, was doing something it should not have been able to do, and the only argument was over which impossible thing. Sit inside that uncertainty for a moment, because it is rarer and stranger than it sounds. We are not talking about a fuzzy object at the ragged limit of detection. The little red dots show up crisp in the sharpest infrared images humanity has ever recorded. We can see them clearly, we can measure their light with precision, and we still cannot tell whether we are looking at a dense swarm of stars or the hidden, screaming throat of a black hole. The clarity makes it worse, not better. Imagine standing in a well-lit room, staring directly at an object on the table in front of you, and being unable to say whether it is alive. That is roughly where cosmology found itself. Thousands of objects, plainly visible, fundamentally unidentified. Their spectra only deepened the unease. Spread their light out, and the shape of it was bizarre. A distinctive V, faint and blue on one side, climbing sharply into the red on the other. And laced through some of them were the signatures of hydrogen gas moving at tremendous speeds. The kind of violent motion you would expect near something with a ferocious gravitational pull. The spectra were not the calm, familiar signatures of an ordinary galaxy. They looked like something caught in the act of a process we had no clean name for. The debate ran hot for years, and only very recently has it begun to break one way. In early 2026, A study built on the very best Webb spectra of these objects offered a new reading of that violent hydrogen. Perhaps the gas was not whirling at breakneck speed at all. Perhaps the broad, smeared shape of those spectral lines came from the light scattering off unimaginably dense clouds of free electrons on its way out, blurred the way a shout is smeared into an echo by a canyon wall. To produce that specific blurring, the objects would need cocoons of hot, ionized gas so dense and so compact that only one thing could plausibly power them from within: a feeding black hole. As one researcher put it, without the ionized gas, the data simply do not make sense. If that reading holds, then many little red dots are young, supermassive black holes swaddled in choking shrouds of hot gas, so thickly wrapped that the usual telltale screams of a feeding black hole, the X-rays and the radio waves, are smothered before they can escape. It is a genuine step forward. It may untangle the star-counting nightmare. But look closely at what it trades away. It solves the problem of too many stars by handing us the problem of too many black holes, grown too big too early. The horror did not leave. It swapped costumes. And even the astronomers offering the new answer are careful to say the case is not closed, that solving this riddle only opens a fresh set of questions about how such black holes could exist at all in the first weeks of the cosmic year. Peel away the little red dots though, and set aside for a moment whether they are stars or black holes, and you find the same hard bone underneath everything. It is not fundamentally a question of what these objects are, it is a question of when they are. The deepest wound Webb has opened in cosmology is not about size or type, it is about time. There simply was not enough of it. The cleanest wound is the galaxy we started with, JADES-GS-Z14-0, because this one is not a candidate anymore. It has been pinned to the wall. Its distance was measured directly by Webb and then confirmed a second way by the Atacama Large Millimeter Array in the high desert of Chile, which detected the glow of oxygen inside it. 2 independent instruments, 2 independent methods, 1 answer. Its light has been crossing space for more than 13 billion years, and it left that galaxy when the cosmos was less than 300 million years old. About 2% of the way through its life, barely out of the dark. And this is no faint smudge of a first attempt at a galaxy. It is bright. It is broad, stretching well over 1,000 light-years across. And it carries oxygen, which changes everything. Because oxygen is a confession the universe cannot fake. The Big Bang made hydrogen and helium and almost nothing else. Every atom of oxygen anywhere, including the oxygen filling your lungs at this exact moment, was forged in the searing core of a star and then hurled into space when that star died in an explosion. So oxygen sitting inside a galaxy is a receipt. It proves that whole generations of massive stars had already been born, burned through their entire lives and detonated, salting the surrounding gas with the ash of their deaths. Not one generation. The astronomers who studied it concluded that multiple generations of very massive stars had already lived and died before the light we are seeing ever left. Multiple generations of giant stars, each one born, each one aging, each one exploding. All of it completed in under 300 million years. Let me make that duration land in your body, because as a bare number, it slides right past. Take the whole life of the universe, all 13.8 billion years, and shrink it down to a single calendar year. On that scale, the Big Bang is the first breath of January 1st. And you, sitting here right now, are the final second before midnight on December 31st. All of human history, every empire, every person who ever lived, fits into the last flicker of that final second. On that same calendar, 300 million years is barely the first week of January. And in that first week, before the cosmic year had really begun, this galaxy had already assembled itself, filled itself with hundreds of millions of suns, and run through multiple complete cycles of stars being born and dying. The slow river model says building something like that takes cosmic months. The universe apparently managed it in the opening days. The lead author of the study, Stefano Carniani, put the timescale into words that are hard to shake. By his team's reckoning, this galaxy seems to have reached the state we observe in something like 10 million years. 10 million years against the billions the model would have demanded. And his conclusion was not a shrug. If that is confirmed, he said, it will be necessary to rewrite the theoretical models of how galaxies evolve. The team searched their entire survey, hundreds of other early galaxies, and found nothing else like it. No analogues. A galaxy standing alone against the theory, holding up a receipt the theory says cannot exist. That is the model's first honest crack. Not a smudge a skeptic can scrub away. Not a photometric guess waiting to be corrected. A confirmed galaxy, oxygen-bearing, fully lit, sitting in the first week of the cosmic year, and doing what the rulebook says takes the better part of a season. And once you accept that the crack is real, the only question left is how deep it runs. Is it a chip in the paint? Or is it a fracture running straight down into the foundation? To answer that, you have to know what the foundation is. And it has a name. The reigning picture of the cosmos is called Lambda-CDM, the standard model of cosmology. And for a generation, it has sat almost beyond challenge. The name itself is a confession of how much of the universe we cannot see. The lambda stands for dark energy, the mysterious pressure driving space to expand ever faster. And the CDM stands for cold dark matter, an invisible substance that outweighs everything we can see by roughly 5 to 1. Every star, every planet, every cloud of gas, every living thing, all of it together is the smaller share. The larger share is stuff we have never touched, never caught, never directly detected. We know it only by its gravity. And that gravity, it turns out, is the reason anything exists at all. Here is the hard truth buried in the model. Build a universe out of ordinary matter alone, run the simulation forward, and you get nothing. The plain gas can never pull itself together fast enough. The expansion of space keeps thinning it out, dragging the clumps apart before they can collapse and ignite, and you are left with a cold, featureless fog stretching forever. No galaxies, no stars, no planets, no you. Ordinary matter on its own loses the race against the clock every single time. So something else had to move first. Something that could ignore the fight ordinary matter loses, that could start clumping earlier and harder and dig gravitational pits deep enough for the ordinary gas to tumble into and finally catch fire. That something is dark matter, and it is the hidden skeleton of the entire universe. It gathered first into a vast three-dimensional lattice of invisible filaments and knots and hollow voids that astronomers call the cosmic web. And only afterward did the glowing matter drain down into the deepest knots of that web to become the galaxies we can actually see. Picture the framing of a house before a single wall goes up. First comes the skeleton of studs and beams, bare and invisible from the street. And only later does anyone hang the drywall, the siding, the windows that make it look like a home. Dark matter is the framing. The stars and gas are the cladding, bolted onto a shape the dark matter drew first. Where that picture falls short is that a house is framed all at once, finished before the walls arrive, while the cosmic web was still growing, still knotting itself tighter, even as the first galaxies were lighting up inside it. The scaffolding and the building rose together, in motion, neither one waiting for the other. And here is the part that matters for our crisis, the part that turns a dot of oxygen light into a threat against the foundation. That scaffolding grows on a schedule, and the schedule is not up for negotiation. The rate at which dark matter clumps together is set by gravity and by the expansion of the universe, two forces we can measure with great precision, and neither one can be hurried. In the early cosmos, the web was still thin. The knots were small and few. The framing had only its first flaws. Lebesgue himself described the standard expectation plainly. When dark matter gathers into a clump, it draws in gas, and that gas becomes a galaxy and its stars. But this takes a long time. and in the young universe there simply were not many clumps of dark matter yet. Not many clumps. Small clumps. A skeleton barely begun. And you cannot hang the full weight of 100 billion sun galaxy onto a frame that has only put up its first few beams. This is the exact point where the massive early galaxies press against the model, and it is not a matter of taste or interpretation. There is a hard ceiling written into Lambda-CDM. A galaxy can only be built from the ordinary matter that has drained into its own dark matter clump, and that ordinary matter is a fixed, known fraction of the clump's total mass. So the number of dark matter clumps in existence at any given moment sets an absolute upper limit on how much starlight the universe is allowed to hold at that moment. It is a budget, and it cannot be exceeded, because you cannot make stars out of matter that has not arrived yet. An astronomer named Michael Boylan-Colchin at the University of Texas at Austin made this precise in a paper whose title alone tells you where the field's nerves were: stress testing the standard model. He worked out that ceiling exactly, the maximum amount of starlight the young universe could possibly contain, and then he laid the most massive early Webb candidates against it. They did not sit safely underneath. They pressed right up against the wall, some of them balanced at the very limit of what was physically allowed. And to reach that limit, the young universe would have had to do something almost obscene. It would have had to take nearly all of the ordinary matter that had fallen into a dark matter clump and turn practically every atom of it into stars. That is the detail that should unsettle you most, because real galaxies never do that. Star formation in the universe we know is wasteful and sloppy. A galaxy pulls in a great reservoir of gas and converts only a small fraction of it into stars before the newborn stars themselves blow the rest away with their radiation and their explosions. The efficiency is low, always, everywhere we look. To approach total efficiency, to turn nearly every available atom into a star, the early universe would have to have been forming stars in a way we have never witnessed in any galaxy, in any era, before or since. Boylan-Colchin's own conclusion did not flinch. Either there is a serious problem with how we think galaxies form at early times, he wrote, or there is a problem within the standard cosmology itself. Within the standard cosmology itself. He put the Foundation on the list of suspects, in print, in a peer-reviewed journal. And that is the fork the entire field now stands at, and it is worth naming as plainly as he did, because the honest disagreement between serious people is the real heart of this story. Either the recipe is broken, meaning the young universe cooked up stars by some radically faster process our simulations never captured, and the timeline itself is fine, or the clock is broken, meaning our whole reckoning of how much time the cosmos had at each stage, the sealed clock we trusted, is telling us the wrong hour, and you can feel how much rides on which answer is true. If it is only the recipe, the crisis is survivable. It means we misunderstood the chemistry of the first galaxies, an embarrassment, a hard problem, but a problem inside the house. If it is the clock, then the Foundation moves. Then the thing we press our watches against, the age and expansion history of the entire universe, is not what we thought, and everything built on top of it wobbles. So the physicists did what physicists do when the ground shifts under a model they cannot afford to lose. They went looking for a way out. Not one way, many. A whole crowd of rescues came rushing forward, each one a different escape route, each one promising to explain how the young universe could burn so bright, so soon, without tearing down the Foundation. Some tried to fix the recipe. Some dared to touch the clock. And every last one of them, examined closely, would turn out to leave a door open that no one could quite manage to shut. Understood. That draft carries the momentum well, but before it goes any further, I need to flag something. Because the whole promise of this channel is that the scariest sentence is also a true one, and a few passages in that text drift past what the science actually supports. Let me set the record straight where it matters, and then hand you a version of these final sections that keeps the dread and keeps the honesty. 3 fixes. First, so we do not lie to the audience. The claim that hyper-efficient star formation violates the physics of gravity itself is too strong. The feedback-free starburst model is a serious, published proposal. It is strained, not refuted. And the framing that the Hubble tension means the age of the universe is wrong overstates it. The tension is real, but most cosmologists do not read it as our 13.8 billion year figure being off by generations. The honest dread is subtler than that, and subtler is scarier. So here is the corrected, cleaned continuation, written to run seamlessly on from where we were, ready for voiceover. The rescues arrived one after another, and each carried the same posture, the confidence of an engineer who is sure the fault is small and local, sure that one clean correction will make the building stand. What none of them expected was how the corrections would begin to argue with each other. The first rescue reached for the recipe. Maybe, it said, the young universe simply built stars far more efficiently than anything we see today. Not 10 billion suns in a galaxy, but 100 billion, packed into dense clusters that formed with a speed and thoroughness we had never bothered to model, because we had never needed to. This is the feedback-free starburst, and it is a genuinely elegant idea. In the ordinary universe, the biggest newborn stars quickly ruin the party. They flood their birth cloud with radiation and blow it apart in supernova explosions, scattering the gas before most of it can collapse into more stars. That self-sabotage is what keeps star formation slow and wasteful. But there is a narrow gap, roughly 2 million years, between the first stars igniting and that violent feedback switching on. And if the gas in the early cosmos was dense enough, the whole cloud could collapse into stars inside that gap, finishing before anything could interrupt it. A fire that burns to completion before the smoke alarm ever sounds. It works on paper. That is the honest verdict, and it is why many cosmologists lean on it. But even the researchers who champion it admit the version that fits Webb's data demands conditions we have never directly confirmed, densities and efficiencies at the very edge of what any simulation predicts. It does not violate gravity, it strains our imagination. And straining is not the same as breaking, which is exactly why the door will not close. You can save the model this way, but only by conceding that the first weeks of the cosmic year were stranger and more violent than anything we can yet reproduce on a computer. The second rescue whispered that the light was a trick of timing. What if the earliest galaxies did not shine steadily, but erupted, brief and blinding bursts of starbirth, flaring like a struck match, then guttering out? A galaxy caught mid-flare would look far more massive than it truly is, because a single burst of very young, very hot stars pours out enormous light for its actual weight. Bursty star formation is real, and Webb has seen it. Some early galaxies that looked terrifyingly heavy turned out to be lighter than they first appeared, their brightness inflated by exactly this kind of flare, and in some cases by the glow of a feeding black hole hidden in their core. This rescue is not a fantasy. It has trimmed several of the scariest candidates down to size, and yet it cannot carry the whole weight. A burst is by nature short. It flares and it dies, choked off by the same feedback that limits everything else. So it explains a snapshot, but not a population. When Webb keeps finding these luminous objects in patch after patch of the early sky, a lucky flare here and there cannot account for all of them. Some galaxies still refuse to shrink. The burst rescues a few and leaves the hardest cases standing. The third rescue was bolder. What if the very first stars were not like ours at all? What if the opening generation skipped the small, slow, long-lived stars entirely and went straight to giants, monsters, dozens or hundreds of times the mass of the Sun, blazing furiously and dying young? A universe top-heavy with such stars would pour out light far beyond what its mass suggests, and it would forge heavy elements like oxygen with brutal speed, seeding a galaxy in a fraction of the usual time. It is a tempting fit for a galaxy like the one we opened with, already carrying oxygen when the cosmos was barely a week into its year. The trouble is that this rescue rests on the thinnest ground of all. We have never directly seen those first stars. Their existence in that extreme form is a reasonable guess, not a measured fact, and there is no independent evidence anywhere else in the sky that the universe ever tilted its star-making so heavily toward giants. It might have. We simply do not know, and building a rescue on a guess about the one population we have never observed is less a solution than a placeholder for our ignorance. The strangest rescue of all turned the picture inside out. What if the light was never from stars? What if these early objects were black holes, already grown large, blazing as they devoured the gas around them, their radiation close enough to starlight across the colours we measure that we simply mistook one for the other. This is the interpretation now gaining ground for the little red dots, and it is technically clean. It fixes the star counting problem at a stroke, because you no longer need impossible numbers of stars, only a feeding monster at the centre. But look at what it costs. It means the young universe was already growing supermassive black holes far faster and far earlier than our models of black hole growth permit. It trades a crisis of too many stars for a crisis of too many black holes. And it hints at something that unsettles the entire order of cosmic history. That the throats of black holes were lit before the sky was full of stars. That consumption came before the calm, slow shine we thought of as the beginning. Notice what happened as these rescues piled up. Each one solved one part of the puzzle and pressed on another. The efficient starburst needs conditions we cannot confirm. The burst explains a snapshot, but not a crowd. The giant first stars rest on a population we have never seen. The hidden black holes rescue the star count only by breaking the black hole clock. Set them side by side and they do not combine into a single clean answer. They interlock into a maze, every corridor doubling back toward the same stubborn wall. And that is when a different kind of question began to surface, quieter and far more disturbing than any of the rescues. What if the problem was never really in the galaxies at all? What if it was in time? This is the edge of the story, and it needs care, because it is exactly the place where honest dread and cheap dread part ways. The age of the universe, 13.8 billion years, is not stamped on the sky. It is calculated, inferred from a web of measurements, chiefly the cosmic microwave background, that oldest light, read together with the expansion rate of space. And in the last decade, a genuine crack has opened in that web, one that has nothing to do with Webb and everything to do with whether our clock keeps honest time. When astronomers measure how fast the universe is expanding today, using nearby exploding stars as distance markers, they get one number. When they infer the expansion rate instead from the ancient microwave background, reading it out of the early universe and running the standard model forward, they get a different number. The two disagree. The gap is small, but it has stubbornly refused to close as the measurements have gotten better, which is the opposite of what an ordinary error does. This is the Hubble tension, and it is real, and it has haunted cosmology for years. It says that either our reading of the ancient universe is off, or our reading of the present one is, or something happened in the dark between then and now that our model does not contain. Now be careful here, because this is where it is tempting to overreach, and overreaching would be a lie. The Hubble tension does not mean the age of the universe is wrong by generations, and it does not mean the early galaxies and the expansion problem are the same problem. Most cosmologists do not think our 13.8 billion year figure is about to collapse. What the tension does is something subtler, and, once you sit with it, more unsettling. It shows that the standard model, the very framework we are using to declare Webb's galaxies impossible, is already leaking at another seam entirely. We are measuring anomalies with a ruler that has its own unexplained warp. Some physicists have started to wonder whether dark energy, the force driving the expansion, might not be perfectly constant the way the standard model assumes. Recent surveys mapping millions of galaxies have hinted, tentatively, that it may have changed slightly over cosmic time. The evidence is not conclusive. It is a whisper, not a verdict. But if that whisper turns out to be true, it would mean the expansion history of the universe is not the smooth, well-understood curve we have been drawing, and the ages we assign to the most distant galaxies could shift, some earlier, some later, the whole timeline breathing in a way we had not allowed for. Picture a photograph of your great-grandmother, the date penciled on the back in a careful hand. You have trusted that date your whole life. Then someone points out that the pen was set by a clock nobody ever checked, a clock that may have been running slow in the years that photo was taken. The face is the same, the date might not be, and now you cannot be sure whether she was younger than the family always said, whether the story you inherited about your own origins was off by a season or a decade. The picture did not change. Your certainty about when it was taken did. Where that image breaks is the scale. This is not one photograph. It is every photograph of the deep past we possess, all dated by the same possibly imperfect clock. That is the true shape of the fear, and it is worth stating plainly without inflating it. We are almost certainly not wrong about the universe being roughly 13.8 billion years old. But we are a very young species, using instruments we built only decades ago, and we have already caught our best model of the cosmos misbehaving in two separate places at once. Galaxies too grown, too early, and an expansion rate that will not reconcile with itself. Neither one alone would topple the model. Together, they whisper that our picture of the first chapter, and maybe of the clock the whole story is told against, is less finished than we let ourselves believe. And here is what that does to your place in all of it. You live inside a story that is still being edited. The number you were taught in school, the age of everything, is our current best reading, offered in good faith and genuinely likely to hold. But it is a reading, not a certainty carved into stone. The people who come after you, 1,000 years from now, 10,000, will look back at our confident textbooks the way we look back at the ones that place the Earth at the centre of everything. Not with contempt, with the gentle recognition that we were doing our honest best with the eyes we had, and that some of what we were sure of was simply the shape of what we could not yet see. The galaxy JADES-GS-Z14-0 is still out there, still burning in the deep infrared, its light still arriving on the mirror of a telescope drifting 1,000,000 miles from Earth. We built that mirror, we caught that photon, we measured it with a precision that would have seemed like sorcery a century ago, and we announced to ourselves that the universe grew up faster than we had any right to expect. The wonder in that announcement was earned, the certainty was not. We do not yet fully know what we are looking at. We do not yet fully know exactly how far back we are seeing. And the most honest thing a scientist can say about the first weeks of the cosmic year is the thing that should sit heaviest with you tonight. Nobody knows. That is not a failure. Sit with the strangeness of it instead. We are creatures who have existed for the last flicker of the last second of the cosmic year. And in that flicker, we have built a machine that can read the light of galaxies that died before the Earth was a grain of dust. We pointed it at the dawn of everything, and the dawn answered back with something our theories did not predict. We could have looked away. We could have filed the anomaly and moved on. Instead, we did the harder thing. We let the universe tell us we were wrong, and we started, quietly, to rewrite the story. That willingness to be wrong, to revise, to keep staring into the dark and demanding that it explain itself, may be the rarest thing in the cosmos. Rarer than 100 billion sun galaxy at the edge of time. Because the galaxy does not know it is impossible. Only we know that. Only we can feel the floor shift, and choose to keep walking anyway. So the question that started this, the one hiding inside a single red dot in a patch of sky the size of a grain of sand, was never really about that galaxy. It was about us. Not whether the universe broke its own rules, but whether we are honest enough, and young enough, and brave enough to admit how little of its first chapter we have actually read. If this rearranged your sense of solid ground even slightly, do me a favour. Hit like, subscribe, and stay for what we take apart next. And leave me one answer in the comments. If it turns out the early universe really did build itself faster than every rule allowed, which would unsettle you more? That our recipe for making galaxies was wrong all along? Or that the clock we measure all of time against was never quite keeping honest time? Take your time with it. We have 13.8 billion years of context, and apparently, not one of them fully explained.